Okay, let's get started. So the stuff that we're about to do is these are pretty hard. There's a lot going on. We're going to be working on application problems, optimization, and then what we'll see next week as related rates. So for those who are going to miss a recitation next Friday, so today, Friday recitation, people, we strongly encourage that you go to another recitation either Monday or Wednesday. Monday and Wednesday these will all be the same content covered. Will be new stuff from what you're doing today. So if you're in a Friday recitation, here's all the possibilities for Monday, Wednesday recitation times. Strongly encourage that you head to a recitation next week before break. Any questions on that? I'll post this as an announcement on Blackboard, all this info. So you can think about that. Okay? Okay, so then if you took the mastery exam this week for second attempt, if you show 90 in Blackboard, that means you passed on the second attempt. If you show a 2, that means you did not pass, and you tried it twice, and we got to do it again. So your third attempt will be in any office hours that you want. So just look at the schedule. So let's say office hours for myself or RTAs, okay? Because they'll have our version of the test. So you're going to go to either my office hours, or Erica, or Julia, or Eugene, and then you can do it again, okay? Gotta pass that to go on. Okay. Any other announcements? Oh, and then there's a recitation handout that you'll either get today or you already have. You're going to turn that in the next recitation, right? So you're going to turn that in. You're not turning that in lecture. You're turning that in your recitation. Okay? Anything else?
The curve sketching.
Yeah. Yeah, so the curve sketching 3-page handout from recitation, you will turn that in during recitation as well. Anything else? Good? Okay. All right, so last time we talked about identifying local max, local min, and rest stops. Rest stops are other situations where the derivative is equal to 0. Or you get a pause in your dependent variable, right? We saw 4 different ways you could get a pause. So what this is really helpful for is what's called optimization problems. So real life problems where we're trying to figure out what the greatest value of a quantity is, or the least value of a quantity. So we're going to start doing these. Talk about this idea. Okay, so optimization. So with a function, various values of the independent quantity can be chosen, and they each result in a corresponding value of the dependent quantity, right? That's just basic function idea, right? Basic function idea. We could choose from a wide variety of values of an independent variable, or we think of that increasing. And then for each value of the independent, there's a value of the dependent. So with optimization, it's kind of like which value of the dependent is the best, okay? And that could be the highest, or the best could be the lowest, right? And so then, in order to find that, we're saying what value of the independent variable should be chosen to attain that highest or lowest value of the dependent variable, okay? So to answer this question, we'll need to know a couple things. What is this function f that relates our independent and dependent variable, the dependent variable being the thing we're trying to optimize? What is this relationship f? Critically important. And then what is meant by the best? So is it the maximum value of f or the minimum value of f? And then finally, in real life situations, you can have this function f, but it only really makes sense on a particular interval of x. What is that interval of x? We call that the applicable domain. The applicable domain is those values of x that make sense in the real-world situation for the function f. Okay? So let's kind of investigate what happens when we're doing an optimization problem here, just in a general sense without having a context. So let's say we want to find the value of the independent variable that would result in a maximum. And so what we're talking about here, you read in the book. Now, what I'm talking about here is what you read in the book, a global maximum. Okay, global. Meaning the absolute highest value. Okay, if the applicable domain is from 0 to 30. So suppose we're going to look at this function f from 0 to 30. And we're going to say what value of x in that applicable domain between 0 and 30 is going to give us the highest absolute value of f. Talk to the person next to you. What value of x is going to give me the absolute highest value of the function f when x is between 0 and 30? Tell the person next to you. Where's Thomas LaCour? Thomas. Oh, he got out just in time. Where's Astrid? Astrid, what did you say? What value of x would give us?
About 5.
About 5. Maybe a little more than 5. Right. Good. And why do you say that? So what is going on at 5? What situation do we have at 5?
Because that's where it's the highest.
Yep. Okay. So that's the highest value of f. And what is that? What is that situation there that we've talked about before? What do we call that? Local maximum, right? Isn't this what we talked about last time? A local maximum. What's true at a local maximum? Okay, but mathematically, we define what a local maximum is. There's mathematical things. Aiden. Okay, that's true. It changes signs. How did we define a local maximum last time? Okay, we said that it pauses, right, for a moment. And so that if the function pauses, then the rate of change is 0. And what characterized the local maximum for us? What did we say? Okay, also, the rate of change is all through there, all through that area of the local maximum. What's the rate of change doing? Decreasing, because the function is turning down. So that means the second derivative is? If this is decreasing, the second derivative is negative. Okay, and what about the function itself? What did we say about the function itself that characterized the local maximum? Remember that? What did we say? Yeah. Okay. Yeah, it has to exist. What characterizes a local maximum, though? Yeah. Increasing, pause, decreasing. Remember this? So the function f increases, pause, decreases. The rate of change is then, before it's what? Rate of change is? Positive, then 0, then negative. And so that means that the rate of change is decreasing the whole time, and so the second derivative is negative. There's a lot to say about a local maximum, right? There's a lot to say. You can talk about the function, you can talk about the derivative, you can talk about the second derivative. Okay, new example. So now, same thing, but now from 10 to 35. From 10 to 35. I want the global maximum in this range, meaning the absolute highest value that f attains between 10 and 35. Go. So what value of x will give me the highest value of f? What value of x will give me the highest value of f? Is Thomas back? Okay, you say? 10. He says 10. Okay, he says 10. Is it the highest value? Yeah. Is it? It's because it's a local max, right? Because it's a local max. Is that right? Is it a local max? No. Local max is f would be increasing, then pause, then decreasing. What is the function doing at 10? Just decreasing. Why is it the global max? It's the highest point, but it's not occurring at a local max. Okay? It's not occurring at a local max. It's occurring at what? The starting value of the domain. Starting value of the domain. It's all decreasing there. F is all decreasing. So the rate of change is all what? Negative. Okay? The rate of change is all negative through there. Next example. 14 to 24. So from 14 to 24. What value of x gives me the highest value of f? $24, right? Is it the local max? Not quite. It looks like the local max is a little bit further over, right? The local max is like 25 or something greater than 24. Okay? Again, so at 24, the function is increasing, so the rate of change is positive through there. So this is what? This local max, or this absolute global maximum is occurring at the left side of the interval. Well, let's do some minimums. 0 to 30. Go. 0 to 30. What value of x gives the minimum value of f? Where's Madison? Grayson? What do you think? What value from 0 to 30 gives the... What's that? Sorry, I didn't hear. 17. What do you think? Agree with that? Okay, so 17 is a local minimum, but is f ever lower than that from 0 to 30?
Yes.
Where? 30. It's 30, right? Yeah, so 30 is actually, you get a lower value than you do at the local min. And what is 30? What 30 is the right side of the interval, right? So it's the end point of the interval. So we should be seeing a pattern here. We're trying to determine, in general, where could these global maxes and mins occur? Because we don't want to test every single x value. It would take too long, right? So we want to narrow down the list of possibilities. So that's why we're doing these different situations. So 7 to 27. 7 to 27. So there's that. It's the lowest value that f attains from x equals 7 to 27. Where's Brandon Ruiz? Brandon. How about Zishu? Zishu, you. Mark Valdez. Mark. What x value gives me the lowest value of f between x equals 7 and x equals 27? Yeah, so right, you're looking at this right here, right? What's that thing called? Local minimum. And let's talk about f first. What's our characterization of a local minimum in terms of just f? What did we say? What's that? Decrease, pause, increase. That defines a local minimum when you talk about f. This is what we did last time. So then what about the rate of change? Or the derivative? Rate of change is negative, then 0 at a pause, and then positive. Okay, so make sure you have this right. The function decreases, pauses, and increases. So the derivative of the rate of change is negative 0 positive. Okay? And then what is the rate of change doing this whole way through here? increasing. The function is turning up, so that rate of change is always increasing. So the second derivative is positive all the way through there, even at the bottom, even at the pause, even where the first derivative is 0, the second derivative is greater than 0 because the first derivative is increasing. Okay, so if we want to, we've got an interval, we've got our function, and we want to find the absolute, or the global maximum in that interval and the global minimum in that interval. What are the possibilities? Through all these examples, we saw that it could happen one of two ways. Yeah. Okay. We saw that it could happen at an endpoint, right? Even if there is local maxes and mins in between, the endpoint of the interval could give us the global maximum or minimum, and also, yeah. We saw that it could happen at local mins or local maxes. So so if we can narrow the list way down of possible x values to the endpoints and the locations of local max and mins, and if we just look at those, if we have a continuous function, then our global max and our global min has to come from that list. So again, to find the best value of dependent, which values of the independent variable should be chosen? Now through what we just worked on, we just narrowed that list way down to a list, right? What is the list of all possible independent variables that might give the best dependent variable value? And we said the critical values, right? Critical values will help us determine local max and local min. So we want to find all the critical values. And what's true about the critical values mathematically? What do we say? What's true about the critical values mathematically? Somebody new. Where is Hannah Arnold? Is Hannah here? Oh, Hannah? Okay. So what's true mathematically about critical values? What did we say? What mathematically defines a critical value? Right. The rate of change is 0. That first derivative will be 0. That was the whole talk on Wednesday was about critical values. The rate of change is 0. So that's one possibility for x values that will give us a global max or min is when the rate of change is 0, or critical values. And the other is the starting and ending values of the applicable domain. Or the endpoints, right? So by creating this list of possibilities, and we could test them. How do we test them? We find out what the value of the function is, right? Given all these, you can find out what the value of the function is. And the highest value of the function will be our global maximum, and the lowest value of the function will be the global minimum. But usually in a given real-world problem, we want either one or the other. We want either the global max or the global min. Okay, does this kind of backdrop make sense for this? And there's a whole other issue to this is conceptualizing these real-world situations, and that's more than half the battle also. Yeah. Okay, so a key element to these problems is going to be getting this function, right? So getting this function, because it's all about then the dependent variable of that function is the quantity we want to find the max or min of. Okay, so I want to talk about, let's go to the book here. I want to talk through an example in the book. Okay, and so it's this situation right here. We've got a sheet of paper, okay? A sheet of paper, a fixed sheet of paper, 38 by 32. And we're going to cut out squares. This is the video. I thought this was a static picture here. There we go. All right, so we got this sheet of paper, and we're going to cut squares out of all four corners, and the squares will be the same size. Okay? So because we have a choice in the matter of how big those squares are, we're going to call those squares x. Okay? So the side length is going to be a value x. Okay, so then we're gonna cut those squares according to our chosen x value. We're going to remove those squares, and then we'll have flaps, and we can fold up the flaps and make a box that has an open top. Okay, so we're going to cut out those squares of our chosen side length and make a box. So is the situation make sense? Okay, so what happens? So we can here's what it would look like if our piece of paper is 38 by 32. That's the red dimensions. And then here's what that box would look like if we cut out squares of 7.11 centimeters. Okay? So for a smallish type square, do you get a tall box or a short box? Taller box or a shorter box? It's more shorter. And does it have a smaller base or a larger base? Larger base. Right. So when you cut out a small square, you're going to get a shorter box that has a bigger base. So then we can go back and take a new piece of paper, and we could cut out slightly larger squares. Here's 8.53 centimeter squares. And so now how will the height of this box compare to the last one? Taller. And how will the base of this box compare to the last one? Smaller, right? So we get a taller box that has a smaller base. New piece of paper. Really big squares. Really big squares result in a taller box with a smaller, narrower base. Okay? So we have the choice of what size squares to cut out, and the result is a different box. And suppose our goal was, so we get, depending on the x that we choose, we're going to get different volumes, right? The volume of this box is going to be different than the volume of this one, and it's going to be different than the volume of this one. So what is our goal? So suppose our goal is to get the largest box possible. With the largest box possible, then we're talking about optimizing the volume. Optimizing the volume. All right, so what did we say? If we want to use calculus to do that, though, we need a function, We need a function with a continuous x variable. Here, it's like this x is side length of the squares. We really can just choose one, and once we choose one, that's the box that we get. So thinking of it this way, we're really thinking of x, the side length of the square, as more of what that we've talked about earlier in the course. It's a constant in the situation, but then we can change that constant value in different situations. What did we call that? Okay, so this is a parameter, right? This is a parameter. We're thinking about our choice of side length, which results in a different box, is really a parameter. Once we choose it, it's constant. And then to make a new box, we got to choose a new one. But in order to use calculus to do optimization, we need a variable, right? We need a variable. So that means kind of reconceptualizing what we just did. Instead of thinking of it as separate boxes from separate sheets of paper, we've got to think of that side length our ability to change that side length and the resulting different changing dimensions of the box that we get. So do you see how that's a little bit different than, so we kind of have to break out of what's real, right? So what's real is we could take a sheet of paper and create one box. But if we want to think about, of all the possible boxes we could create, and we want to find the one with the best volume, then we have to reconceptualize this of how the box would change as we gradually change x, which is kind of like impossible. But in order to solve that problem of what's the maximum volume we could get, we need a function. So we need a function. So we need to think of it this way. So that's the way we want to approach these problems, is we want to first think about static situations. Static situations and relationships statically, and then from thinking about maybe a few different static situations like we did, then conceptualize the situation dynamically, meaning what would it be like if it were possible for us to change, for instance, like these squares that we're cutting, change them gradually, and what would be the result? Because now from that we can develop a function, right? A continuous function of which we'll have a volume. So now we could write volume as a function of x, where x is a gradually increasing side length, which is kind of physically impossible. But it's necessary for conceptualizing this function, right? Gradually increasing side length. Again, and then it's the same thing we were talking about earlier in class. So what value of x will give us the biggest volume? What value of x will give us the biggest volume? Okay, so actually the book is very, very thorough in solving this problem. So I'll leave that example for you. We won't go through the book. We'll do a new example. But I just wanted to use that as a setup to get started here. So let's review this kind of approach to solving these problems. So strategy for optimization problems would be, maybe it'd be better if you wanted to take notes on this, that you would do it through the video later, and pause it so you could really listen and be thinking about what I'm saying and what you're reading, rather than trying to write, okay? So conceptualize the situation statically. This is step zero. Step zero, so it's like we're not even really into the problem yet. But this may be the most important and maybe the longest step. It would be step zero. Conceptualize the situation statically. What quantities are constant but change from situation to situation? And then write relationships between these key quantities. Okay? And this may be the longest step of the whole problem. Okay? This may be you spend the most time on this. Then we want to envision the situation dynamically. Okay? So reconceptualizing the key parameter as a variable. So for us, in the box problem, that was the side of the square cutout. Have to imagine that thing growing gradually and the resulting box, how it changes. Okay? And so then we're going to define a function with a dependent variable being the quantity to be maximized or minimized. Okay? And so then our whole solution then is revolving around this. Steps 0 and 1 are to get to this function, and then the rest of the steps are going to use that function. So this is kind of the centerpiece of the solution. It's this function whose dependent variable is the quantity to be maximized or minimized. Okay, and so then what are we going to do? We're going to look for what are two possibilities where we have local max and min, and so then along with that, we want to define the applicable domain. So let's put that in there too. So when we say define the function, that also means when we say define the function, that includes defining the applicable domain. The interval of x, which makes sense in the context. Okay. And if we want to find the local max and min, that means we're going to have the derivative is where it's going to be 0. So we need that derivative. We need that rate of change function. Okay, and so the critical values of the independent variable of the function. So we're going to have the local max and min, and we're going to have the endpoints of the applicable domain. Okay, Sometimes, some situations, that applicable domain won't be finite. It's possible, theoretically, that it could be an infinite domain. And then in that situation, we're specifically looking for local max or local min, okay? When that x interval is infinite. Okay, and so then we're gonna find the global max or min by testing our critical values and the interval endpoints. Okay, so this is going to be our approach. So let's look at a couple examples here. Any questions on what we've talked about? And again, oftentimes you should be spending most of the time on the problem in step 0. You want to really understand the situation. We've talked about that earlier in the semester too. You really want to understand the situation that you've got. Drawing pictures and identifying a static situation, maybe a couple, 2 or 3 static situations, and then so that we can then reconceptualize those static situations as gradually varying, although that's like physically impossible. But we need that for the function, okay? Step 0, though, is going to be our key thing. So here's an example. A rectangular storage space is to be created against the building using 84 feet of chain link fencing. Fencing will comprise 3 sides of space, and the building's wall will form the 4th side. Space must not be narrower than 4 feet. What configuration of the storage space maximizes its area? So what I want you to do first is I want you to, can we draw 3 possible situations or scenarios that fit the criteria of the problem, right? So you have some set criteria here for what the storage space would be like. So can you draw 3 different possible setups for this storage space? Sketch them, and then label them. Label them with the quantities. Okay, label them with quantities. Okay, so draw 3 possible storage spaces that fit this criteria. Go. So this is step 0, right? We're orienting ourselves to the problem, thinking about it statically. So I'm not giving you a picture because often you won't have one. You've got to start picturing this in your head and making the sketches yourself. That's a key skill, okay? So that's what we're doing. We're making sketches of 3 different configurations that are possible. All right, so let's just see what you're coming up with here. So you have a building, and you're putting this thing. Show the building and the space. Does the length of the wall change with the different storage spaces? Some of you are showing that your wall length is changing along with the storage space. Okay, and I actually want you to pick values. Pick values and then label all values that you know. Okay, so actually pick values so that you get a particular configuration and you know exactly what all the, what is this area? So what the length, find out what the lengths are of your, and then what the area is. Also find the areas for your three configurations. All right, where's Haley? Haley Nadone. Haley, 2 lectures in a row. So what was one configuration that you came up with? What was it? So is that good? So, but is that going to work? 20. So 25 this way, and then 34, and then 25. Is that going to work? Yeah. Okay. Yeah, it does. 25, 34, and 25. So your building is just right. So we just imagine that the walls go on. Some of you are drawing just rectangles. So that kind of, the rectangle, that would kind of indicate that the wall, the width of the wall is changing, right? And that's not true at all. So we just have this wall to set it against, and we'll continue on. All right, so she said 25 and 25 and 34. Okay, and so what's the relationship? Why does this work? So why does this work according to the criteria? What relationship is there between the 25 and the 34 that makes it possible? What's that? Yeah, so right, so like 25 plus 25 plus 34 equals 84. What about the area? What's the area? How would you calculate it? 25 times 34, whatever that is. Okay? Where is Glenn? Firm. Glenn, give me another one.
I did 10 on the top and the bottom, and then 64 on the side.
So 10 and 64 and 10. Does it work? The little tick mark is, if you're not familiar with that, the prime, that can mean feet. So maybe I should write feet, but anyway, I'm using the prime is a shorthand for foot. Okay? So, again, what's the relationship? 10 plus 10 plus 64 equals 84. Area equals 640 in this case. All right, one more. Where is Ryan Husker? Ryan here? How about Jacob McLean? Jacob McLean. Jorge. Avila.
He dropped.
Thank you. Hannah Everman.
She dropped.
Lucas Erickson. Lucas, is that you? Did you get another one? 35, 35, and 14. Awesome. Again, 35 plus 35 plus 14 equals 84. That's plus, and then 35 times 14 is whatever that is for the area. Okay, so what's the narrow, so like this one is getting really long and narrow. What's the narrowest it could be? 4, right? So it could start at like 4, and then what would the length be? 76. Okay, and then what would be the extreme other situation? 40, 4, and 40. Okay, so now we can configure. So how many different ways could we do it? A lot, okay? So can you conceive what it would look like? So now we want to think of this varying, right? So what is our variable that before was fixed, and each individual situation was fixed, but now we want to think of it varying, and as it varies, the configuration of it changes. So what will we use for our variable? What do we think? Any ideas? Let's see. Where is Riley Rayburn? Is Riley here? Riley? Is Riley here? How about Tsunomi? Regmi? So what could we use for our variable in this situation? Okay, so pick one. So which side do you want? The horizontal side. What do we want to call it? The horizontal side length is? We could call it x, okay? So somewhere in the middle here we have more of a squarish one. So x feet. That makes this x feet also, right? And so now, what is, in that first situation, what is the value of x? Here x equals 4. Here x equals 40. And so really we just found the applicable domain, right? We just found the applicable domain. The lowest value of x could be 4. The biggest value of x could be 40. And so, can you imagine that if we were to change x, the configuration would change along with it, right? Along with it. Okay? And so, what is this then? So this dimension we can call y if we want. It's fine. So now we're in step 1. We're reconceptualizing this as variable, as that horizontal dimension is going to vary gradually, and it's going to start at 4 and it's going to end at 40, and what's going to happen to y as x increases? It's going to decrease, right? It's going to decrease, so that what relationship holds true between x and y? Right, so this is this first thing we did every time. So it'd be 2x plus y equals 84. Okay, and what is the quantity that we're trying to maximize or minimize? That's really going to be what our function is about. So what is that quantity that we're trying to maximize or minimize? Area, right? So area, and what does the area equal? That was our second. x times y. So this is kind of our starting point for our area function, which is now we're in step 3. And step 3 is we want to write area as a function of, but the problem with this is it's now a function of 2 variables, and we need it to be just a function of 1. Notice, the quantity that we're trying to maximize or minimize is the dependent quantity of this function. This is the key. The function we're trying to write, its dependent variable is the quantity we're trying to maximize or minimize. In this case, we're trying to maximize area. So we want a equals xy, but really what we want is a as a function of just x. Right now, it's a function of x and y. We need it to be just x. So, how do we get from this being x and y to just x? Yeah? Right, now here's where this comes in. So this comes in, this gives us what y is in terms of x. And if we can get y in terms of x, now then we can rewrite this. So this important relationship, it's not the function we're focused on, but it's going to help us build that function. And it tells us that y is 84 minus 2x, which allows us to write our key function a in terms of just x. So y is 84 minus 2x. And so we got it. Can I erase what I wrote so I have some more room here? Can I erase? So if a sub x is x times y, or x times 84 minus 2x, and that's 84x minus 2x squared, and we know we're going to go from 4 to 40. That's the applicable domain here. X can be from between 4 and 40. So what are all possible values of x that could give us the maximum area, right? It could be x values that give us a local max, and these x values 4 and 40. So to get the local max, we're going to take a prime. And we want places where the first derivative is 0. That's going to pinpoint our local max and local min. So what do we get? Is that 21?
Yeah.
So now we have x equals 21. That's either a local max, it's going to give us a local max or local min. We have x equals 4 and x equals 40. So this is our list of candidates. This is our possible list of candidates for the largest area. So what do we do? Yeah, we're just going to check those. We're going to take a of 4. We're going to take a of 21 and a of 40. We've got the endpoints. We've got the local max and or local min. And so then the largest value of those, which is going to be this one actually. So whatever that value is the largest possible area, and then we know how to configure what is 21. 21 is that value of x, that's horizontal dimension. So 21, 21, and 42, is it 42? So what's 21 times 42? 882. So a of 21 is 882 square feet. Okay, so Blackboard for homework. We're going to start working these problems. Due Wednesday. Due Wednesday in lecture.